This is the final video report for Brady Allen and Brandon Packer for our project in ECE5320 Mechatronics. For this project, we created a simulation of an inverted pendulum using MATLAB and Simulink. We recorded this video earlier, and I'm going to go through now and do a voiceover and go through some of the details of what is going on in this video. Starting off, we show the interior of the sensor subsystem block, where we add noise to the states coming out of our pendulum dynamics. The pendulum dynamics simulate the full nonlinear equations of motion of the inverted pendulum as well as the motor controlling them. We can switch between the true states and the sensed states using this manual switch. We also have a to file to store data to be used for plots, a subsystem block that is used for animation, a position slider to change the position of the pendulum cart while we are running the simulation. Looking inside the controller block, we can see we have built two controllers, one LQR and one PID controller, and we can also toggle between the two controllers. This first run we will be doing is using the true states and the LQR controller. We will also move the desired position to show that functionality as well. You can see the position is able to move as we desire it to. Here are the output plots showing the actual versus desired cart position. The pendulum angle obviously is desired to be 0 or straight up, and it also shows the control voltage. Moving on, we switch to the PID controller. We've tuned our PID controller slightly differently in order to achieve a faster response on the position, but at the cost of some overshoot. Here are the graphs from that simulation. These graphs from that simulation. You can see there is that the theta doesn't quite settle out as quickly, and there is more overshoot in the cart position for the PID controller. We're now going to do the same run, but using the sensed states, and what you'll see is that there is a little bit of chatter. It may not be obvious in the animation, but the graphs will show it, especially in the control voltage. So now we are switching to the PID controller. Doing the same run, we'll be able to see some of that chatter in the graphs. Now what we are doing here is, in the bottom left, we are changing the length of the pendulum after we have calculated our LQR gains. One of the disadvantages of using an LQR controller is that they have a very limited band of operation in terms of parameters. They work very well for the parameters that they are calculated for, but once you stray from those parameters, they can quickly become unstable, as we will see in these next two runs. This problem doesn't exist quite as severely with PID controllers, because PID controllers have much wider gain margins and much wider ranges of operation in terms of parameters. So what we have done is we have calculated the LQR gains using a length of 1, and then we have doubled the length to be used in the actual dynamics of the system. So as we can see, it attempts to stabilize, but in this case it is unable to do so, and it quickly saturates its control voltage. Now switching to the PID controller, we can see that there is a little bit more oscillation, a little bit more overshoot, but it is able to eventually stabilize both the angle and the position. And you can see from the graphs it is converging to the position and also to the theta, and this is also on the true state, so you can still see the chatter in the control voltage. Overall, the takeaway lesson from this was that the LQR controllers are very good controllers, but they also work in a very limited band. If you are going to use one, then you need to make sure that all of your parameters are exactly correct, or you may run into instability issues when you implement them in real-world situations, mostly because of their very tight gain margins. They work very well in a very small region. The PID controllers would be able to work for a wider range of parameters, and there are times when you may or may not know exact parameters, and in that case you would definitely want to use this PID based approach, because as we can see from the simulation, it is able to work even if you've changed some parameters. So this makes it a superior choice for us as a candidate for real world implementation.